You might need to help him if he has questions over these problems. All right. Today, I have just a little bit to say at the end of section 1, and then we'll launch section 2, which is really what chapter 5 is all about. So 5.1 continued from Friday. Just a few things. We have something called the monotone convergence theorem. I'm going to state it. It will be fairly obvious, I think. We're not going to prove it. We have other courses here at Fox where we do approach these things a little more theoretically. Because it's not going to be hard for us to believe. We're not going to prove it. So here I have a sequence referenced by the A's. This sequence is monotone. And remember, that means it's either an increasing sequence or it's a decreasing sequence. It's even true if we say eventually, but we won't say it in the theorem. And we need one more thing. It's bounded. And it converges. So here's an example of a sequence, not a very interesting one, which is increasing, and just the sequence n, but it's not bounded. Terms themselves head off to infinity, and it diverges. As opposed to, in just real simple ones, that sequence, 2 minus 1 over n is an increasing sequence. As n goes to infinity, 1 over n gets smaller. Right? So we're subtracting less away on each term. This is increasing. Is it bounded? Yeah, can you tell me a bound? 2. Yeah, all the terms are less than or equal to 2. And bounded. Therefore, it converges by the theorem. Now, because it's a simple sequence, we really don't need this theorem. We can see those terms, the 1 over n's are going to go to 0, and it will converge to 2. But sometimes we can use this theorem to prove that a given sequence converges, even though we may not know the value it converges to. If I can show it's increasing, one way we can show a series is increasing is if I replace the n's with x, think of it as a function of x. If that function is differentiable and its derivative is always positive, then it's increasing. And so we might use some things you know about derivatives to settle an issue, increasing versus decreasing. But we haven't had to do it yet. We'll see. We'll hold that in our back pocket just in case we need it someday. All right, here's another thing left over from section 1. I want to investigate this sequence for any real number R. So if I write the term down, it's like R squared, R cubed, on and on and on. Real simple. What I want to know is for what values of R does it converge? And what does it converge to? And, I want to totally settle the issue. I want to know when it converges, and I want to know when it doesn't converge. Okay? So let's just play around here a little bit. There are a couple of boring cases. What if R equals 1? What does our sequence look like? It's just 1, 1, 1. Does it converge? Move down the list. You get like super close. Yeah, we're stuck on them. It's a boring sequence, but it converges to one. It even feels like, because it's stuck on one, like it's not really converging. It is one, but we say the word can converge because it has a limit. Okay, like it's so boring, we never really even think of it in this language. All right, how about r equals -1? What's the first term if n starts at 1? And then
1.
and what do you think? Converge or diverge? The values do not approach at all. They just hop back and forth. Now, this is not a very interesting sequence, but we're going to make good use of what's going on here. And that is the fact that -1 to the n alternates sign. We're going to see it again because of that fact. That's all it does. It doesn't change the value. It changes it from positive to negative, but mostly alternates the sign. We're going to use it that way. How about if r equals 1/2? So my sequence is 1/2, comma
1/4.
1/4. I think skip 1.
1/8.
8. 16. Converging or diverging? It looks like it's convergence. And what value does it converge to, do you think?
0.
0. What is about 1/2 that made it different than -1 or 1? But can you give me another value that might have similar behavior? 1/4, 2/3. Now you set any fraction? Because the math teacher, I think, well, fractions can be proper or improper. I think you're meaning exactly the right thing. You mean a number less than 1. Think of that as a fraction. Yeah. In fact, for every real number as well. Here's the facts. If r is between r and 1, including 1, it converges. If r equals 1, it's a very boring series, it converges to 0. The interesting ones, not really here, but the things we're going to do with them, these guys, it converges, and it's going to converge. I'm sorry, I got ahead of myself. You noticed it. That one stuck on 1 forever. This is the one that converges to 0. If r is bigger than 1, the terms shoot off to infinity, right? 2 to the n, 2, 4, 8, 16, off to infinity. If r is negative and less than -1, they get big in absolute value, but they keep alternating. So none of those are interesting. They diverge. Now they diverge differently, but they diverge. So these right here are, in fact, the ones that are going to become important to us. As well as this little thing right here, this little algebra way that we can alternate signs. We're going to use that as well. It may be a while before we use that book as well. Okay, so 2 important findings here. We'll use. The second one we're going to use today. First one we'll use eventually. Any questions? Are you willing to believe that as long as r is between -1 and 1, that sequence converges? All right. I think that concludes what I needed to do from section 1. That's section 2. The title here is Infinite Series, which you may remember is my title to chapter 5. Not the author's title. Should be, but it isn't. All right. Here's what an infinite series is. I told you on Friday the word series means add, not obvious. Right? Never, in no other part of English does the word series mean add, but it does in math, especially in Calc 2. It goes something like this. I have a sigma, which is the very same sigma we use for Riemann sums. That led us to the addition there. And I have an index just like there, and starts somewhere. It doesn't have to start at 1. Most of the time it will. The difference between these and Riemann sums is going to go to infinity, and then we have a sequence whose terms we're adding up. Okay, something like that. So this stands for this addition problem. On and on and on. And what we want to investigate, that's what an infinite series is. And what we want to investigate is when does it add up to a finite number? That is, when does it converge? And when I say when, it depends on, all depends on that formula, a sub n, right? The terms that it's telling us to add up. When does it converge? If it does converge, can we find the value it converges to? Early on here, we'll be good at it. Eventually, it's going to become very hard for us. We'll be able to prove it converges, but not really have enough tools to find the value it converges to. Later on, we'll add some tools that will help with that. But that's the issue. We're going to add these things up, an infinite number of them, and we want to know, does it add to a finite number? Or does it not converge? It can converge by adding up to infinity, one direction or the other. Or it could just get into some oscillating. I'll show you examples. Now, you can't literally add an infinite number of numbers. But we have a tool we've developed that helps us do mathematics at an infinite level. We've used it at least twice before, specifically for this reason. When we started talking about derivatives, we wanted to find the slope of the tangent line. Well, the slope formula doesn't work for that because we only know one point on the line. So remember, we got a nearby point. We found the line through those 2 points. It wasn't the slope of the tangent line, but when I made this point slide in arbitrarily close to this, that's an infinite process as well. It got me the slope of the tangent line. So the limit covered the infinity there. And then when we started talking about area under curves, we approximate with rectangles, right? We can do that. But to get the exact area, not an approximation, how many rectangles did we need? An infinite number. We can't really add them up. So we found a way to use a limit, again, to do the infinite work for us. It's what we're going to do here as well. It's really, there are other things, but it's one of the primary ways that limits help us do the work we need to do. So I want to start with the definition. Given this infinite series, I want to define something called the sequence. It's sequence of partial sums. So every infinite series has associated with it a sequence of partial sums. We're going to give it a name. We're going to dedicate the symbol S. I'm going to use sequence notation, but the only time I would ever use S is in connection with an infinite series, okay, which has its own sequence. The A's would provide the numbers we're going to add together. And here's the way it goes. It's a sequence. S sub 1, the first term of the sequence of partial sums, is the first number in my infinite series. Not very interesting. S2, however, and just think about the words. A sequence of partial sums. And think about the fact that we need to learn some ways to deal with the infinite series because I can't handle the infinity. I can add up the first 1,000 terms of it, no problem. It's going to infinity, that's a problem. So this partial sums, it's like we're going to work our way up. S2 is A1 plus A2. It's a partial sum, very, very partial. Only the first 2 terms. What do you think S3 is going to be? Now the sum of the first three. It may come in handy later. Notice I can write that as S2. The sum of the first two embedded in S2, and then we'll just tack on the third. And so on. The nth term is the sum of the first n, which I could also write as Sn minus 1. I'll say n, right? I know that when we learn math, study math, feel like it's all about the numbers. The words aren't important, but the words are crucial. Every day you study math, the words become more and more important. Maybe not so important back in grade school or middle school, but now the words, and just think about it. This thing tells us what it is. It's the sequence of partial sums. And I think about that and what we've said here, it makes sense to us. And now, how do I go from the sequence of partial sum to the infinite series? So what we're going to do is say, just like we did for the slope of the tangent line, just like we did for areas, we're going to start the sum terms and then let the limit take over. Okay, so the sum of this series, I equals 1 to n, a sub n, is going to be the limit. Then goes to infinity of its sequence of partial sums. So that's our definition of the value of an infinite series. We're not going to add an infinite number of numbers together. We're going to find a formula. Write it out to you. That's what S sub n is. And does it make sense that to find the infinite sum, if we could take the limit as n goes to infinity, I feel like that's going to do the job, just like taking an infinite number of rectangles, filled out all of the area under the curve, and that we couldn't really write out the areas of all those rectangles, but we could find a formula for it and then take the limit, right? Just like we did for integration, just like we did for the slope of the tangent line. Does this intuitively speak to your heart? Does it make sense to you? It should. And super good words. That for integration, it wasn't such a great word like Riemann sum. What in the world? Riemann was just some guy, right? A German that lived way back when. But here, ordinary English words, sequence of partial sums. We know what they mean. We can put them together and understand how it leads us to this guy right here. And then all we need to do, my mistake, should be an infinity. I'll give you 30 seconds to pick your notes. I hope some of you wrote infinity because we knew what we were talking about. This would also be, again, I confused my partial sum notation with series. Either one. Right. So if we're going to make this work, we have to do two things. One of them is really hard to do. But it's going to be easy. And when we're going to use it, and then when it starts getting hard, we're going to find other tools to use. Okay, the first thing I have to do is find S sub n in a form that I can take the limit. What we know about it, it has these dots in there. Ellipses, I think, is what we call them. And we did not learn anything in Calc 1 in all of our work with limits, and we did a bunch of work. We did all of Chapter 2, and then we came back to it in Chapter 4 once we learned about derivatives, and we applied L'Hopital's rule. But nowhere did we learn how to take a limit when there's a dot, 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 right? We need a formula. We need a function, and then we can do it. So that's the first problem we have to solve. The second one is just finding the limit of the thing that we end up with. It could be challenging. Tegan asked me to do number 12 because that was a challenging problem. So we could run into the similar kind of a challenge once we get our formula for Sn. But that's what we have to do, to find the sum of the series. So are you with me? Yeah, most of you are trying not to make eye contact. So then I might ask you something. I hope it makes just super good sense. It doesn't mean applying it, problems are going to be easy. Hopefully they'll be challenging. I mean, that's what we like, right? It's a good challenge that we can rise to. But hopefully the notation, the way we use limits, exactly like we use them in Calc 1 to get us to deal with the complications of infinity. I say exactly like it, the details are different, but it's the process is similar to how we did it in Calc 1. All right, I want to take a look at a special case of a series, geometric series. Geometric series lands right in the sweet spot for us because it is a series where we can find a nice formula for Sn. Nice meaning we can get it and we can take its limit. And the other thing about it is, at least in the work I do, it's an important series in applications. There was a problem on the homework. It doesn't feel like all that big of a deal maybe, but it asks you to find the sum of a series that's generated from a physical process. I'll let you read the homework to figure it out. Because I'm not going to have time to do an example like it in class, I actually did an example on the board in my office and I posted the worked out solution. So don't go there first, read the problem, try to figure it out yourself. Only if you devoted 45 minutes to it and still haven't really made progress, then go look at the solution that I posted. You'll be a whole lot, even if you don't make a lot of progress in the 45 minutes, you'll be better off for having tried to do it yourself. And there's lots of other things I could do. Just a simple dice question could lead us to needing to solve an infinite geometric series to answer the question. I'll do an example, not today, but later. All right, so here's what a geometric series is for us. It's a series that can be written in this form. We'll start at 1, take A times R to the minus 1, where A and R are real numbers. Which if you just look at that formula, plug in the first few values, you see what's going on. To move, the first term is A, and it equals 1. 1 minus 1 is 0, R to the 0 is 1. And then as n increases, just add in another multiple of R. So total means A plus AR plus AR squared plus AR cubed. On and on. I'm pretty confident that you all studied finite geometric series in high school. Better have, or your teachers didn't treat you right. But we want to take, going to do the same kind of things, but apply it to this infinite series. All right. So how do we analyze this? Well, here's how we do it. we need to find a formula for S sub n that does not have dots in it because we don't know how to do the limit there. And then if we can find that formula, then hopefully we can just take the limit. If we can do it, we've solved the series. Okay, so here's how we do it. There's a little trick that calculus teachers know that maybe not every student knows. S sub n is the sum of the first n. It's a finite series. And when n gets up to, when the exponent gets up to n, or S sub n, then we just get a r. Maybe I should have written what S sub n is. That's what it is. And if I write the terms out, it looks like that. Jesse. Pardon me? Yeah, I did it on purpose here. It's exactly like this. Because I want to write the nth term, which means I need to sum up to n. Well, I need me a variable that takes me up there. So I use some other variable, I or j or k or whatever. I should use j, that's my favorite one. But I use that. Okay? Just write out first in terms. That's all I did. You can write it in sigma form or not. Doesn't matter. It's easier for us, I think, to see what's going to happen if we don't write it in sigma form. So I wrote this here because that's the way we saw it over there. And then I wrote the terms out, whichever way. Now here's the trick, and it's not obvious. When I was sitting in my Calc 2 class, I would have never dreamed this up on my own. But if the teacher said, "Hey, let's do it," like, okay, I'm all for that. Let's do it. I might even in my head, I would say, why in the world would you do it? But, that might be a stupid question. I'm going to multiply through by r. Both sides of this equation. So I just get RSN on the left. And then multiply by r will distribute. All the powers are going to go up by 1, including getting an r on the first term. Let's say that step requires genius. And, I'm not talking about me. Somebody showed it to me. That person was maybe not a genius. 200 years ago, if we could trace it back, we could find the genius. His name was not geometric. The series gets the name for other reasons. But someone a long, long time ago figured it out. And the rest of us have just thought, well, that's a cool little trick. I think I'll do that. All right, now subtract. This equals that. This equals that. Therefore, this minus this equals that minus that. That might be the transitive property of subtraction. We've done it all the time in algebra, systems of equations. We do it all the time, which gets me here. The left-hand side is really easy. Sn minus Rsn. Well, what happens on the right? Blue. This guy is only on the first equation, not on the second one. So he's going to survive. But then I get plus AR minus AR. What happens? Yeah, they add up to 0. AR squared minus AR squared. 0. What's the next term? AR cubed minus. All the way down. This guy cancels there, but there is nothing up here to cancel that. So we get A minus A r to the n. So what we just did here, that thing, we might see it again. It's called telescope. This is like taking a telescope and putting it back together. Jesse.
What is your A R T N?
Well, if I would write out the term right before this one, I would get AR. Yeah, you can see we got this diagonal canceling on. But nothing to cancel that guy out and nobody to cancel that. Okay? Notice the dots are gone. That's what telescoping did first. Now let's factor out S sub n here. And let's factor A out there. And finally divide by 1 minus R. So we found a formula, and not a very complicated formula for S sub n. Nth term of the sequence of partial sums. So the series is the limit as n goes to infinity. That's our definition. Well, this is a constant. A over 1 minus R doesn't depend on n. We learned in chapter 2, we can take that out. Using 1 minus R to the n. And what is that limit? Well, it depends. If R is between minus 1 and 1, strictly between, what does R to the n do? How do you know? Who else said it? Jesse, how do you know? Okay, Daniel, how do you know? Did you say it goes to 0? Oh, did you say it, Ken? Really, how do we know that? Yes, there's a better way. Noah. So what is the very first thing I talked about in class today? After we talked about homework, we talked about the sequence R to the n. Why did we do it? Well, you didn't know, but I did. We're going to run into it. And I wanted you to be prepared. So, Jesse, you're thinking about, and I think Scott was too, why you're thinking about why is it what it is? When I want you to say, oh, we did it, like 30 minutes ago. We worked it all out. This guy right here goes to 0 if R is between minus 1 and 1. We just worked it out. Okay? So if minus 1 is less than R, less than 1, then the limit S n is equal to A over 1 minus R. R to the n goes to 0, which makes this limit just 1. So right here is just 1. 1 times A over 1 minus R, that's A over 1 minus. The only other value for which R to the n converged was if R equals 1. Remember, we got this boring sequence 1, 1, 1, 1, 1. Well, if I plug in R equals 1 back into my geometric series, R equals 1, it's going to be A plus A plus A I'll say, is that going to converge if you add an infinite number of A's up? Are you going to get a finite value? Absolutely not. You're going to get infinity times, A times N. It diverges. So let's summarize the geometric series. So whether you understand anything I've said or everything, you absolutely have to know this. Summation n equals 1 to infinity, a r to the n minus 1 equals, converges to a over 1 minus r, if and only if r is between minus 1 and 1. It diverges for all other r. I did something here. I'm not sure I've done it before. We identified that an infinite series, it's a limit. It may converge. It may diverge. It may exist in the language of limits. It may not exist. If it exists, if it converges, then, and we know the value, we always say the series equals the value. Okay, so this equal sign and no infinity over here tells me that series converges. And it tells me the value that it converges to, a over 1 minus r. Okay? So I said a little bit ago, like whether you understood everything I said or nothing that I've said, you absolutely have to know that this is true. Okay, let's practice. First, I'm going to tell you something without justifying it, and I'll spend some time on Wednesday. Let's take a look at what happened. If you write out the initial geometric series that I just erased, then you'll notice that A, the numerator of our solution, if r is between minus 1 and 1, it's the first term of the series. So let's think about that. In the numerator, we have the first term. And in the denominator, we have 1 minus the value of r. That works for the given series, as long as it's strictly between minus 1 and 1. So that's the way we're going to think about this. A geometric series. I'm going to start it at some number, I don't know, c to infinity. If we can write it in the form, that form, whatever the power is, it's going to converge to the first term divided by 1 minus. So it doesn't really matter what this number is. We can start with that number and plug it into our formula. We get the first term. And then the series converges that. Let's do some examples. Find the sum. I'm going to give you all of them that converge on the homework. Some do, some don't. The ones that don't, in the end, are not interesting. It's important for us to recognize, but they're not going to be important in the long run. Let's start with the super easy one. 4 times 2/3 to the minus 1. That has absolutely perfect geometric form. And what's r? 2/3. 2/3. Is that a good one or a bad one? Does it converge or diverge? Converges, yeah. What does it converge to? Well, the first term, 4 over 1 minus r. That fast. See, it's geometric. This one is easy. We're going to run out of time, but I'll do at least one more where it's not so easy to see it's geometric. I'll help us through it, but then we'll find R.
What's the symbol that's a 2/3?
Say it again.
The symbol that's a 2/3 sigma.
This guy, that's a 4. Here it is, a prettier one. I like pretty answers. I'm going to multiply top and bottom by 3. 3 minus 2. That series converges to 12. One more example. This will be super helpful to the homework. Summation n equals 2 to infinity 5 times 2 to the n plus 1 divided by 3 to the power n minus 1. That does not look like a geometric series. It just has more stuff going on, but we're not going to panic. So what I'm going to do is pull one of these 2's off. I want to get the power n, not n plus 1. So I got a 5 there, and then I'm going to pull a 2 off, and then I have 2 to the n in the numerator. See how that works? I'm going to make numerator and denominator have the same power, and then I can combine them. Now, I'm short of 3. I want n of them. I'm missing 1. So I'm just going to multiply top and bottom by 3. So this 3 survives. But then I can put this one there, and I get 3 to the n. See how that works? You never knew in 4th grade when your teacher said, you can multiply by 1, and it doesn't change anything. Like how often we would use that. Every day we use that. I've seen some fuzzy looks, but not out of time. All right, 5 times 2 times 3 is 30. And now I get 30 times 2/3 to the n. Now it looks geometric, doesn't it? A r to the n. A r to the n. A is 30, r is 2/3, the same as this problem, coincidentally. But this one starts at 2. You know, maybe there should be a -1 here to make it just have a beautiful form. It had a -1, but remember, r equals 2/3. That's a good one. It's less than 1. So it's going to converge. It's going to converge to the first term. So now I look over here and say, okay, my term started 2. So I'm going to get 30, doesn't depend on that 2, but this does, times 2/3 squared. That's the first term. Just plug 2 in. And divide by 1 minus r. And that is the value that converges. All right, so it's kind of, here it is, written better. So in the homework, you may need to go through some process where you're verifying that it really, in fact, is a geometric series. But once you get there, A r to the n, that's the key, A r to the n. Then that's our sum over there. The value converges to the first term over 1 minus r. All right, see you Wednesday. Your homework is posted.